All right, so today we are going to do spatial analysis and mapping in R. Now, a quick note, R is not necessarily the best program to do spatial joins or really complicated spatial analysis, but R is fantastic for quickly visualizing spatial information and looking at how data is distributed with relationship to space. So in order to do mapping in R, and mapping is actually kind of a computationally heavy thing, so we have to install a lot of packages. Um, Before we install any packages, you need to update all of the packages that you have because the Dippler package that you have installed is most likely out of date. There was a big update in February of 2018. So before we do anything, we are going to update our packages. It's actually really easy in R to update your packages. You just type update dot packages and open close parentheses, and you can actually hit Command Enter if you are on a Mac, and that will run whatever line your cursor is on. When you get this option here, hit Yes. Down here in the console, hit Y, and just keep hitting Yes until you get through all of the packages that you're being asked to update. It'll probably take a few minutes depending on the speed of your connection. While that is running, come back up to the document here, and we're going to start installing our packages. First one is ggmap. Install packages, ggmap. It's just like ggplot, but for maps. The next one is the maps package. Install packages and then maps. And it looks like we have a few warnings down here. It doesn't look like there were any major errors, so I'm going to assume that it is all okay. If you have any problems, it's probably written out in that error message, but it also probably updated a whole lot of packages, so it'll take a little bit to sort it out if you end up having any problems. All right. Install packages map data. We're going to install packages SF and install packages SP and the GG themes package. And the Census Tracts comes in the Tigris package. Tigris. And we want the TMap package, which is going to allow us to do some joins and other functions. And finally, we're going to install leaflet down here. All right. So go ahead and run all of these. Just hit highlight them all and hit Command Enter. And then we're going to start loading them. So I want the tidyverse. We want library lubridate, because we're going to be dealing with our dates. We want the leaflet library. We want the ggmap library. We want the TMap library, TMap. We want the Tigris library. We want the SP library and the GG themes library. And the map library, maps. And we want the map data library. There are a lot of libraries when you are working with maps, and we want the SF library. All right, SF. All right, go ahead and run all of these in order to pull in all of those libraries, and then we can get started. All right, so we're getting data from a variety of different sources. They're all linked here. We have the data beta, the NYC Open Data, which is an excellent repository of a wide variety of data sets, and from the city of New York. All right, so the idea of maps in R, or really any GIS software, is really similar to the idea behind ggplot library, that you are layering a base map and putting data with some sort of associated geometry. So as you are building your map, you can think of it in the same kind of layered format as you would think about a ggplot, where on the base for a ggplot you have your Cartesian plane. For a ggmap, you have some sort of a base map. Again, if your goal is to do spatial statistics or draw buffers, R is not your program. But if your goal is to layer data on top of a base map, R is ideal. The first type of map that we're going to use is actually pulled in through the Google API. And in the handout with this, there is the link to go and register yourself for the Google API. There is also the link to my API key. So I am not going to type out my API key, but in order to register this session with Google Maps, you go ahead and type in register Google and then key equals, and then type in your key here. And like I said, if you are on the LMS, you can borrow my key for this purpose. Please do not store my key permanently in your workspace. If you are going to use this more than this tutorial, make sure that you go out and register for your own API key. They will ask for a credit card, but it is highly unlikely that you are going to make enough API calls to ever be charged. But they are going to ask for a credit card, which is why for the purposes of this tutorial, I will let you borrow my key. After this semester, I will destroy that key. So it'll only work for this semester. All right, so once you have registered your key, you can go and load a map of New York City. So we're going to get this map by using the latitude and longitude, and we're going to pass that as a location to the function getMap. Right? So if you look up where is New York City on the internet, you will find that New York City is at longitude about -74. I'm going to put in -73.95, and latitude about 40, 41. I'm going to put in 40.69. All right, and that's our latitude and longitude for New York City. It's actually a list, so you need a C out front. All right, and then I'm going to call my New York City map, and I'm going to call the function getMap, and I'm going to pass it my location, which will be New York City. This is my starting location, and a zoom level 10. Zoom level, as we talked about in class, refers to web maps and how close you are to the location, or rather how much of the world is being shown given how many tiles you have. For more information about that, go back to the course notes. And our scale is going to be 1. Scale is just the resolution that Google Maps reads this map in as. All right? So I'll go ahead and run those two. And it makes an API call, and it will load a map shortly over on the right-hand side. And it takes a minute. You may have this warning about the time zone. Don't worry about it. That just means that the time zone in your version of R has not been specified, and that's okay. All right, and once you see this arrow down here, then you can make the final call, which is ggmap, and then pass it New York City map. And this is how ggmap knows to actually display your map. It tells, hey, go ahead and display yourself over here. Excellent. And we have New York City, our zoom level 10, and it's a pretty low resolution. We could up that if we were on a stronger internet connection. We also notice that there's this very interesting thing that ggmaps does, which is puts out the latitude and the longitude as if it were plotting it out in a Cartesian plane. The x and the y are the longitude and the latitude here. That's not always ideal, so we will address that in a later part of this tutorial. But just know that the way that ggmaps works is really built on top of ggplot, hence why it by default passes you these axis labels. The other thing to note is this is in pseudo-Mercator because that's what all web maps are, which is what allows us to have this latitude and longitude along the y-x coordinates. All right, so what's really interesting about this is that if you look here at the source, and it says source, maps, Google APIs, and it tells it where the center is and the zoom is. If you go out to an internet browser and you look at a website, what you see is this exact same structure. So what you see here is that I just went to Google and typed in New York City, and Google Maps brought me back to this google.com maps place, New York, New York, and here is my longitude, and here is my latitude, and then this 10 is my zoom. The rest of the information in the rest of the URL is just additional information about how Google Maps renders the image. But you see that in every map that you call on the internet, this information, this longitude and latitude and the zoom is recorded in the URL, which is just pretty cool. All right, so what I'd like you to do now is take a second to play around with the zoom, play around with the scale, and see how you can make this map slightly different. All right, so welcome back. We've successfully played around with our base map. You might be a little bit closer in, a little bit further out. Now we're going to add some data on top of that base map. So I'm going to ask you to call noise311 and set that as a variable for our 311 data from NYC Open Data. This is a data set of noise complaints from the 311. So this is people calling in to say that, the music is too loud or there's construction or things like this. So my CSV is on the desktop. Go ahead and navigate to wherever yours is at. And it is called 311 Service Requests from 2010 to present, which is not at all true. What this is a data set of is only 2017, and it's only about 3 months worth. Because the data set is huge. So there is tons and tons of 311 service requests. I highly encourage you to go out to the NYC Open Data and download some of these and play around with it and see if there's any variables that are interesting to you. For us, we are going to focus only on noise complaints during this 2-month period, because it's just an example data set. All right, so we have said read CSV and then told it where to find it, and we'll set header equal to true because we do want it to read in the headers. Hit Command Enter to run it, and I want to see what it looks like. So I'm going to glimpse noise 311, and I'll run that. And what I see is that I have a whole lot of variables here. I think it's actually 53 variables. And it's things like, we have our latitude and our longitude, so this is important. We also have a location variable, which is just the latitude and longitude combined. We have all of this other location information that's primarily not relevant for noise complaints. We have the complaint type, a descriptor. Notice that both of these have been read in as factors rather than as characters. We have the incident address, which is additional information on top of the latitude and the longitude. We also have this address type, which is really interesting. We have block face, address, intersection, and I think those are our three. And we have a description, which we already said. We have a unique key, which is going to be really important for us to make sure that we preserve that and never drop it and never change it. We also have a created date, which was read in as a factor, not as a date. All right? So there's a whole lot more that we can play around with here, but it's not totally necessary. You'll notice that we have 53 variables, and we're not going to use all of those. We also have almost 31,000 observations. That's kind of a lot. All right, so let's start working with this a little bit. The first thing that we want to do is filter out any column that has only NA values, because that's not going to be helpful to us at all. So I'm going to write a function, and I'm going to call my function not all NA. And it's going to be function x, where if any is not is NA, I'll break this down in a second, of x. All right, let's break this down from the inside out. So I have x. If x is NA, we get a true, right? If this exclamation point means the opposite. So if there is an NA, we get a false. So if there are any falses, then we want to return a false, right? So I'm going to call that on my noise 311 clean, or my noise 311 clean is going to be my noise 311 filtered by, so piped over to, select if not all of the columns are in NA, right? So it's going to call this function on every column in the noise data set. And if all of the values are NA, it's going to return a false, and then it's going to return false for that column. It's going to say, do not return that column. All right, we go ahead and run that, and we will look at our noise 311 clean, and we will glimpse it. So glimpse our noise 311 clean, and we have 38 variables here. And we see that it remained, the unspecified remained, but all of those other NA columns were omitted. We could do another round of this for the unspecified, but for the time being, we are going to let it be. All right, so now that we have our 38 variables, we probably want to change our dates. We're going to be using LubriDate to change our dates. All right, so we're going to call our noise 311 clean, and we're going to call our created date. And we're going to set it to month, day, year, underscore hour, minute, second. So we noticed here that the format is month, day, year, hour, minute, second. Pull that back down. And then we will pass it the noise 311 clean created date. And I'm just going to copy it and paste it here. Okay. And I want to do the same for the closed date. So I'll do noise 311 clean, $ closed date, and I will assign it to month, day, year, hour, minute, second, noise 311 clean, closed date. right? And I will run both of those. And we should see nothing out, but when we glimpse our data set again, we should see that our dates have been read in as dates and are no longer factors. And we see that here. We have a date timestamp here rather than a factor. Excellent. All right, so we are making progress cleaning our data set. Now let's go ahead and plot these points and see what we get. So we're going to add a point layer to our base map here. And we'll call ggmap on our New York City map. And just like with ggplot, we will add to it a geometry layer. We'll add geom point, and our aesthetic will be longitude for the x and latitude for the y. And our data will be from noise 311 clean. Okay, run that. And we see over on our map that these are a lot of points, to the point where it is not very informative at all. So with this many points, you probably want to filter down to just one type of noise complaint. So we're going to look at noise complaints that are only about ice cream trucks. We want to know who is complaining about ice cream trucks. So we are going to use the string R package, which I forgot to load earlier. So I'm going to go back up to where I've loaded all of my libraries, and I'm going to add another line, and I'm going to have library string R. I forgot to load that library. All right. Come back down here, and we are going to search for only those columns that have, or only those rows that have ice cream truck in our descriptor. So we want to look at what all of the values in our descriptor column are. So we'll call unique, noise 311 clean, and only the descriptor column. So go ahead and run that. And it'll take it a second to run, but we see here that we have alarms, air conditioning, barking dogs, all kinds of different things that people complain about. So we are going to pick ice cream trucks. You are welcome to try picking another one, but for the purposes of this tutorial, we're going to use ice cream trucks. All right, so let's transform our descriptor column into a character column. So we'll go as.character, and we'll pass our noise 311 clean, and then our descriptor. The other thing that's really interesting in this data set is the resolutions, how people write up how these things got resolved, because that data is created primarily internally. So it's really quite cool, honestly. All right. So the descriptor column was transformed into a character column rather than a factor. And now we're going to make an ice cream data set, ice cream 311. And we will assign that to our noise 311 clean that is filtered by str detect. So we are looking for, in our descriptor column, the phrase ice cream, written exactly how it's written in the descriptor column with the proper capitalization. Okay. So if we run that, we find all of the columns that have the ice cream type, no matter if it has other data in it as well, or if it's just a complaint about the ice cream truck. All right, so let's take a look now at the dimensions of our new ice cream data set. So dim ice cream 311, awesome. This is going to be way easier to work with. It looks like we have about 1,000 records and only 38 variables. That sounds far more manageable for such a small map than 31,000 records and 53 variables. All right, so now let's look and see if there's only one kind of description for ice cream or if there's multiple. So we will go unique ice cream 311. We'll call descriptor. We'll run that, and it looks like there's 15 levels, but the only descriptor is actually the noise ice cream truck with the code NR4. Awesome. So it looks like we can use this directly. So now that we've narrowed it down a little bit, let's see what our map looks like. So we'll call ggmap, and we will call the New York City map, and we will add to it a geometry, a point geometry, geom point. Our aesthetic will be the same, longitude and latitude. And then our data will now be the ice cream data set. So ice cream 311. Run that. And this is much easier to deal with. Once we zoom in on this a little bit, we'll probably be able to get a sense of where these complaints are coming from. Notably, there are no complaints here on the Staten Island Greenbelt. Very few complaints out here in Queens, but a whole lot of complaints right up here in this cluster. All right, cool. Much better, and we can probably work with this a little bit more easily. But we could do a little bit better. The first thing that I would like us to do is change the zoom, increase the scale, and play around a little bit like that. So I'm going to assign my New York City map to get map, and I'm going to have my location still be New York City. I'm not going to change that, but I do want to change my zoom up to being 11, and I'm going to make my scale equal to 2. Right? So I'll run it, and this should pull in a new map scaled in a little bit closer. It did not give me a new map a little bit closer. Because I haven't called my map yet. Right, okay. So we will call the exact same ggmap. I'll just copy and paste it here. I'll run it again. And you notice here something really interesting. So we've gotten a warning message every time we've called this map, right? So the first time, our warning message was that it removed 20 rows containing missing values. And we just kind of breezed over it and didn't address it. Here, it said we removed 121 rows containing missing values. What's going on with this warning message is that there's not enough space within the bounding box here to display all of the points on this base map. So you see here some of Queens, some of the Bronx, and some of Staten Island all got cut off in going from zoom level 10 to zoom level 11. If your focus is here kind of on the central area of the city, then that's fine. If you need to show the entire city, then you might want to go with zoom 10.5 or something like that to make sure that you're actually showing all of the points and you're not cutting any off. And you'll get this warning message anytime you cut some points off of your base map. So if you have data that you're laying on top of your base map, you'll get this warning message. All right. So far, if we've been doing things kind of in a shortcut way. So if we make our maps this way, we end up having to specify our data every single time. It makes it redundant, but possibly more importantly, we're not able to do faceting. So this is actually very easily solved by adding a base layer function. So we're going to call ggmap again, and we're going to pass it our same New York City map. But rather than immediately calling our geometry, we're going to call our base layer. And we're going to call it within our ggmap call. So rather than a plus sign here, we've used a comma. Okay? We call New York City map, and we say, hey, your base layer is going to be a ggplot of the ice cream 311 data set, where the aesthetic every single time is going to be the longitude and the latitude. And now I can add multiple layers of this data without having to recall the data every time. So now I can add a point geometry. I can add a geom point, and my aesthetic will be color is equal to address type. Right? So I have this base layer that every single time this base layer is the latitude and longitude of and longitude of these points, and then I can layer address type and complaint type and resolution type on top of it. Right? So I'll run that, and we see here that we are now looking at our base layer, which is these points, but we've added in this address type variable with 3 colors. It's a categorical variable, so color was an appropriate choice. And the address types are address, block face, or intersection. So we can see where people typically report from addresses here in northern Staten Island, southern Brooklyn. People typically report from intersections. It looks out here in Elmhurst areas, more intersections. And it looks like the block face is not so common of an address. We have one out here by the airport, one out here in Brooklyn, a couple in the Bronx. All right, so this helps us see, where different types of complaints are made. And we may, through the course of our research, come to understand that maybe these are different types of complaints. Maybe complaints that occur from an address are of a different nature than complaints that occur based on an intersection. All right, so there's, this is all right, but it'd be really helpful if we could see this broken apart. If we could see the addresses, the block faces, and the intersections mapped separately. We actually already know how to do this. It's just faceting. So I'm going to copy this map again, and I'm going to add faceting. So I will add a facet wrap, and I'll facet by address type. And as we expect, we should see this broken down, and we'll get 3 maps by address type. One for block face, one for address, and one for intersection. Excellent. There we go. And this is great, but this longitude and latitude is really not necessary. It'd be really helpful if these could be removed. So we're going to do a little bit with theme. All right. So, and right now this kind of looks like a blob, and we can't really tell it apart. And this is redundant, to facet by address type and to break it apart by color. While that emphasizes our point, it may not be necessary. So let's make a bunch of changes to kind of tighten this map up a little bit. So we're going to call GJ map again, and we're still going to call our New York City map, and I'm actually just going to copy this map call here and paste it here and edit from there. Okay, so here we could probably use color better. Rather than having address type as color, I'm going to say borough, which will kind of help us break up these very small maps that we're looking at. And if we're still faceting by address type, it should be no problem to see that. In addition to that, I'm going to specify a theme, and my theme is going to be the void theme. Theme void takes every single thing away. No legend, no axes, no titles, no nothing. There's just no information around your map. So we're going to need to add some of that back. So we do that by adding theme And then we do actually want a legend, but we want it to be at the bottom. It would be, it's taking up too much space over here. We'd prefer to make this take the full width. So let's add our address down here on the bottom. So we'll say legend.position will be bottom. And we do still want a title. So our plot title, we will specify as element text and horizontally justified, hjust, equals 0.5. By default, GG Maps, GG Map plots, put the title left justified, but generally we want to have our plot title in the position in the middle. So calling plot title does two things. It returns the title to our theme, and specifying that it's h-justified, horizontally justified, 0.5, puts it in the middle. All right, and then we want to add some labels. So we call labs, and we'll pass a title. We want our title to be ice cream noise complaints 2017 by address type. And our caption will be source NYC open data, because we should always say where we get our data from. Ideally, you would hyperlink this, but for our purposes here, that's not really necessary. All right, so now we will go ahead and run this whole thing. And takes a second to load. But now we see we can visually break up our boroughs a little bit in these very small maps. We have our legend down here, we have our title up here, and we have our source of where we got this data. Stretching this window, it takes a second to reload, but we can start to see, that the noise complaints are clustered around here, that we have a whole line of addresses right here. It's not as easy to make a comparison about where the different types of complaints are, but it is very easy to see that blockface is not so common, and there's a lot of similarity between address and intersection. All right, so rather than, so I want you to, for your assignment now, to trade out address type for borough for both the color and the faceting. Does it make sense to trade out, to switch the color to address type and the faceting to borough? Why or why not? And what combination of visualizations between color and faceting makes the most sense to display address type and borough, and to still be able to compare across versions of the same map? So if you don't have a good intuition on this, go ahead and try it out both ways, where you have borough for both color and faceting, address for both color and faceting, and color equal to address and faceting equal to borough. All right, so take a few minutes and play around with that, and then we will move on to interactive and thematic maps. All right, so once you've played around with the faceting and the variables a little bit, we are going to move on to making interactive maps. R has a package to work directly with Leaflet, which is a web mapping program, or web mapping package that draws on the OpenStreetMaps. So the way that you work with Leaflet is you first call Leaflet, and then pipe it over to the add tiles command, and this is how you get your base map, and then pipe it over to set view, and then from set view we need to re-specify our latitude and longitude. So I'm going to specify it as negative 74.00 and 40.71, and I'll put my zoom equal to 12. Go ahead and run that, and we get a slightly different map here. This is the OpenStreetMaps base, which you can call a whole bunch of different OpenStreetMaps map types. I will let you go ahead and play around with that in the leaflet documentation. This is just to let you know that you can make interactive maps with leaflet. All right, we are going to move on to yet one more map type, and this is going to be to make thematic maps. So if we wanted to join different spatial data sets together or calculate the relationship between them, we would use the TM map package. TM for thematic mapping map package. Right. So we are going to make a list of the New York City counties. And if you don't know what counties are in New York, we have New York County, that's Manhattan. We have Kings County, that's Brooklyn. We have Queens County, that's Queens. We have Richmond County, that's Staten Island. And we have Bronx County, that's the Bronx. Okay. And then we're going to call New York City tracts. Now, this is actually really, really cool. Remember at the very beginning, we loaded the Tigris library. What the Tigris library allows us to do is to pull shapes directly from the Census API. So we are going to call tracts, which is what calls the Census Tracts, and our state is going to be New York, NY. You can also pass it the number 36 because New York is number 36 for the census. And then we'll pass the New York City counties. And what we're going to say is pull in every single county, and CB equals true. I have long forgotten with CB why that's necessary. But whenever you are pulling in tracts, you have to pass CB equals true. All right. So this has told us what numbers, what FIPS code is being used for each one of our variables. So 36 for the state, and then all of these numbers are the code for each one of these counties. All right, so we've loaded in our counties and our tracts. Now let's call summary on those tracts and see what we get. So it has told us that it is a spatial polygons data frame in the S4 mode. Most spatial objects in R are of this S4 mode, and they are spatial polygons data frames. What that means is that there's spatial data that has the instructions to draw a polygon. So it's kind of like a data frame, but it's a special type of data frame that tells you, okay, so put a point here and then draw a line to this next point. So not only does it have all of the points, but it also has the order that each one of those polygons should be drawn. All right? So if we plot our NYC tracts, there's no NYC tracts up there. So if we call plot on our NYC tract, what we should get is a simple line plot that shows us all of the tracts for New York City. And we can click on zoom to see it much better, and you can actually see all of the census tracts in the city. A census tract is approximately 2,000 people, give or take. Don't worry too much about that. It's really just a way that the census divides up physical areas. So we could get deep into how census tracts are made, but for our purposes, all that it matters is that it's a unit of land that has a lot of data associated with it from the US Census. All right, So let's look at what one of these things looks like. So we are going to look at the head of NYC tract and pass n equals 1 because we only want to look at one of these things because they're huge. Okay, so it is of the spatial polygons data frame. We already said it has one feature. Here are the bounding box. So this is the area all the way around it. It's not the instructions to draw it, but rather it's the area around it. The coordinate reference system that it's in, how many variables it has associated with it, and what types of information are available in this data frame. Now, if we wanted to very specifically only check on what projection it was in, say we really wanted to join this data frame or this spatial object to another spatial object, they would have to be in the same projection. So the way you can check on projection is proj for string and then pass NYC tract. Run that. And it looks like I have forgotten to have us load a package. I did forget a package. So go back up to the very top of your program, up here to where all of the libraries were loaded in. And I made a typo. Library TP, that's here in line 19, should be library SP. So go back up to the top, change library TP to library SP, and then rerun that road or that line, and you should have library SP was built under R version 3.4. All right, so now we go back here and run this line proj for string NYC tract. We'll go ahead and run that, and this tells you the projection. So it's telling us that we are in WGS 84000. This is telling us that it is quote unquote unprojected. Unprojected is not really a projection as we talked about in class, but this allows us to join to a lot of other data sets. It's just not always the best way to display your data in the end. All right, so we are now going to load in some income data. So if we're going to call income, set the variable income, and we'll do read CSV, and you should have pulled this down from the LMS, and for me it's on my desktop in the data sets, and it is called median household income census tract.csv. It has headers in it, so header equals true, and we'll run that, and we'll take a look at what that data set looks like. So glimpse income, and we'll run that, and we see a whole bunch of variables here. We see this FID, don't worry about that. The state, so this is New Jersey. There's also New York, the tract number, the GeoID, all of these different information. What we are interested in is MHI, which is median household income. But we don't need all of this stuff. We only need the tracts that are in New York City. So we're going to join this data set to our spatial data frame, and through that, only select the tracts that are in New York City. Okay, so this merge won't work if anything is duplicated. So we're going to start by checking our different tracts. And we know that we want to join by tract, so let's try out this variable, tract CE10. So we'll go ahead here and we'll type any duplicated, and we'll pass it income. Oh, I am typing in the wrong spot. Sorry about that. We'll go here. We will type any and duplicated, and from the income data set, we will ask if the tract CE10 has any duplicates. And we see down here that it says true. So we don't actually want to use the tract column or the tract variable because it has duplicates. So that's not a unique identifier. Let's try this GeoID 10 and let's see if the GeoID is an appropriate variable for us to use. So we'll call any duplicated and we'll pass income, and then we'll call the GeoID 10 and we'll see if that. No, there are no duplicates in the GeoID, so we can use that as a unique identifier. We just have to make sure that it's in our spatial data frame. All right, so let's set a new variable and we'll call it NYC Tracts merge, and we will assign it to an SP merge. So we are going to call the package with merge because there are other merges specified, but we want the SP packages merge, not any other merge that comes in with any other package. We're going to pass it the NYC Tracts, and we are going to pass the income, and our X column, so by X equals GeoID, and by Y equals GeoID 10. And our New York City tract has this GeoID column, our income has this GeoID 10 column, and they're actually the same GeoID. The 10 refers to the 2010 census. So what's going on here is that you always join with the spatial object first, and you join the income or your CSV, your data set, to your spatial object. So go ahead and run that. If nothing happens, you did it right. And let's check it out. Let's glimpse our NYC Tracts merge. We'll run that. And it looks like we have a whole lot of spatial information. But we also have attached to it all of this information that came from our income data set. The county, the percent of people that own their homes, the median household income, all of these variables. All right. Excellent. So now we can make a very nice chloropleth map with our new data set. So we'll call TM shape, and we will pass it our NYC Tracts merge, and then we will add to it a TM fill, and the column that we want to specify is the median household income. We'll run that, and we should see a very nice chloropleth. And it'll probably take it a minute. There we go. So here we have a chloropleth of the median household income broken down into 6 categories, also with a missing specified, a couple missing census tracts out here. And this is great. The only small problem is that it looks like Manhattan and Queens are connected. And we know that there's water on that, and we should have some sort of visual cue to break those up. So I'm going to add a water file. So this also comes from the Tigris package. It comes from the Tigris API. And I'm going to set a variable called NYC Water, and I'm going to call area water, and I'm going to specify New York and NYC counties. And what this does is it pulls the water areas from all of the counties that I had specified in my New York City counties. And then once you pull that in, and then if we copy this, paste it down here, and we're going to add to it another shape, TM shape, and we'll call NYC Water on that. And we'll add to that a fill, close our parentheses here outside of that, add to that, just as we did before, a fill, and the fill will just be a solid fill. So our color will be based on gray, will just be gray 90, which is just like a base gray color. So we'll run that. And it'll take it a second to load because it's pulling on all of the variables together. And excellent. We've made a visual cue to say that we are breaking apart Manhattan and Queens, and we are breaking Manhattan from New Jersey. This water up here technically belongs to New Jersey, which is why it doesn't get pulled down in this with this. If you're making this map for publication or for a final project, you do actually want to pull out the water shapes for that county. So it's a matter of going out and finding out what that county is. Okay. The next thing we would like to do is add a title to our legend. So I've copied this again, and here our fill color is based on the median household income, but MHI is a pretty abstract title for our legend here. So we are going to say, for this fill here, we're going to put the title is equal to median household income to overwrite that MHI. And we can go down here and run it again, and that'll fill in the median household income. All right, so looking at this, what do you think is going on out here with this very dark shade, or very dark census tract, and these couple of very dark census tracts here? If we zoom in on it, you can see it just a little bit better. We have some census tracts by the park where the median household income is 250 to 300,000. Down here at the southern tip of Manhattan, and one out here in Staten Island. So take a couple of seconds to think about that, of what factors could be contributing to that. Isn't necessarily the case that there's a lot of very wealthy people in all of those tracts, or could there be anything else going on, depending on how much you know about Staten Island. All right, so looking at this map, if you live in New York, you probably don't think about New York in terms of census tracts. You probably think about New York more often in terms of neighborhood tabulation areas, or NTAs. NTAs are things like Harlem, the West Village, Lower East Side, Astoria, and things like that. Sunset Park, Park Slope, Bay Ridge, Sheepshead Bay, Bensonhurst. Obviously, I live in Brooklyn. So you probably think about New York more often in terms of neighborhoods rather than census tracts. We can actually pull in a neighborhoods file that also comes from the NYC Open Data. You can get this file from a lot of different places. I'm going to call this file NTA, and rather than read CSV, I'm going to read OGR. And read OGR allows me to read spatial files. So this is also on the LMS. And if you call desktop and info 640, this is where I obviously keep all of them. And it is called neighborhood tabulation areas. And inside of the neighborhood tabulation areas folder, there is an SHP file. You'll notice that there's 4 files. Do not delete any of these files. You only have to load in one of the files, the SHP, the shape file, but the other 3 are essential to stay in the same folder in order for the shape file to be read. Without the other 3 files, the shape file cannot be read. So make sure that you download the entire folder together, not just the one file. All right, so If you run that, you get an error that says that function read OGR is not found, which means that I forgot to load yet another package. So if you go up to the very top of your code again, you need the rgdal library. So we will install .packages rgdal. This allows you to read the file in, and then go down here and call library rgdal. The read OGR function is in the rgdal package. I'm really sorry about that. So once you've loaded your library, go ahead and run this line again, and you should have no problem. It should say OGR source with driver, and then tell you where the source is, and tell you how many features and how many fields are in that data set. Okay, excellent. So once you've loaded your rgdal package, come back down and rerun this line of code. Rerun the reading in. Excellent. Okay, now good practice is to ask what projection this new file is in, and it looks like it's in a similar but not exactly the same shapefile. If you are ever not sure, best practice is to take your new file and assign it to an SP transform, and we are going to transform our new file, our NTA, into the same projection, the proj4 string, of our old file, of our NYC tract. Okay? And this will make sure that the new file that you're reading in lines up with the file that you're layering it on top of. So it's good practice to always, whether or not you think that they might be in the same projection, just transform your new file into the old file's projection. You can do it the other way around, but then you'll have to reload your old file again. Okay, so now let's plot the neighborhood tabulation areas over the census tracts. So we will call the same function that we've been calling. So I'm going to go up and copy it and paste it down here. And I'm going to add to it, I'm just layering on top, the TM shape, and I will pass that NTA, and I want that shape to be TM borders. And I'm just going to have the borders. I don't want anything else. Go ahead and run that. And this makes it a little bit easier for us to understand, to kind of see patterns in different neighborhoods and see how income affects how we define our neighborhoods. Excellent. Now, a logical next step would be to group these census tracts together by neighborhood tabulation areas. In the interest of time, we are not going to do that during this tutorial. This requires a few transformation steps since we need an equivalency file that maps tracts to neighborhoods, so we can take our NYC tracts merge, add to that a neighborhoods file based on tracts. So for example, tract 1 might be Upper West Side, tract 2 might also be Upper West Side, tract 3 might be Upper East. You see how this goes. So you take this equivalency file, merge it with your tracts file, and then group by the neighborhoods. And then map that to your neighborhood boundaries. Now, that's more work than we're going to do right now, but you do have all of the skills to do that based on what you've learned here and in the data cleaning and data visualization tutorials. It's not difficult, it's just a lot of steps. So we are going to skip that, and we are going to move on to tidying our map. So we want to add a title to the fill column. We might want to change our palette, and we want to make sure that we specify where we got our data. So I'm going to use the code that we've already written as my base. I'm going to change my fill to the red palette. So I'm just going to specify palette here. And I'm going to say reds. You could choose blues, greens, purples, whatever you would like. I'm going to make my borders for my neighborhood tabulation areas a little bit wider. So I'm going to go down here to my shape NTA, my borders here. I'm going to say color and set that equal to gray 30. You don't need to know what these are. These are all in the documentation for the TM Maps package. You can play around with this as you like. And I'm going to specify my line width equal to 2. So I'm going to make it just a little bit wider. And I'm going to add to this a TM credits. And I'm going to say my source is the 2010 census 5-year estimates. Or it's, yeah, this comes from the 5-year estimates from the 2010 census. Go ahead and run that. And it takes a second to load. While it's loading, we are going to want to save our map. So I'm going to say save _ tmap, and I'm going to specify my width equal to 6 and my height equal to 10. And this is going to save to the location that you are running your, that R is installed on. You can also use this export button and you will get the same result. So I'm going to go ahead and save that. And what that does is it saves this entire map that we've been calling this whole time. All right. So from here on the LMS, you'll find a 2010 Census Tract demographics cleaned, and use this, pull this data set in to make another choropleth map visualizing another one of the metrics. And it might be the number of males or females, education level, any of the variables that you find in the 2010 Census Tract demographics cleaned. So for this tutorial, go ahead and submit another choropleth map based on another one of those variables. And you can go ahead and change your line widths and things like that here, since the very large line width is not actually that attractive. It's just really for illustration. All right, let me know if you have any questions. And in the physical handout of this tutorial, there's quite a bit more about how to go about using interactive maps, adding layers on top of them that did not fit into today's video. All right, have fun working with your maps and enjoy. All right.